from the player, just to the process and those things.
Good afternoon. I was asked to work on some review problems which does not look like the exam problem.
No, just give us the example.
That's-
Say thank you.
we work on some problems as long as time allows us. So I will start with the first problem.
Dr. Hubby, are you going to post these problems?
I can do that, yeah.
I could.
All right. Let's take a look at this mechanical. There is a pipe AB, which has been connected by this cable at point D. Point D has a distance of 80 millimeters from the top surface of the pipe. The diameter of the pipe is 60 millimeters. As you see, the radius is 30, with the thickness of 4 millimeters. Just think, if you are tightening this cable, so if you just tighten this cable, it's gonna make the tension force on the cable with the magnitude of 18 kilonewtons. So the cable DE is gonna see 18 kilonewton force applied to that, meaning at point D, this pipe is gonna see 18 kilonewton in this direction. So if this is the pipe, point D, if this is point D, which can be applied, which can be connected to the pipe AB, is gonna see the force of 18 kilonewton because it has been connected to this cable. So we would like to see if this pipe can support this load or not, or if the failure occurs or not. The pipe is made of, just giving you some information about the pipe, AISI 1020 hot rope. And we were asked to find the factor of safety. And see if failure occurs.
No point C.
Pardon?
Where's C on that?
Yeah, A, B, D, E, H.
I don't see point C. I don't
Okay, then.
I just wanted to make sure.
And this distance, I mean, there is missing one distance, which is dB. dB is 400 millimeters. So from point D to point B, which is the end of the pipe, we have 200 millimeters. So dB, from D to B. So first, I will find the projection of this force in this direction and this direction. This direction is Z, and this direction is Y. So this angle is 70 degrees So this angle is going to be 20 degrees. So F in this direction, Fz is going to be 18 kilonewton times cosine of 20, and F in y direction is going to be 18 kilonewton times sine of 20. It's making 16.92 kilonewton, and it's making 6.16. Now I'm looking at each individual force to see what kind of stresses these forces are making over this pipe. Let's start with FC. What would be the first stress that you can see FC is gonna develop over 5 kb? Compressive stress. It's gonna push. So Fz is making compressive stress. The stress is going to be sigma. The direction of this is z, sigma z. So at which section is gonna you are gonna see the maximum compressive stress? Each section is gonna see the same compressive stress because force is going to apply to cross section, so it's going to be the same for any single cross section. So what else? Do you see any other stress that this force can make? This force has this distance from the center of pipe, 18 millimeter here, 30 millimeter here. It's going to be 48 millimeter. The force is going to act in z direction. This is going to be in y direction. So z times y is going to be in x direction. Mx would be f. The force is acting in z direction.
Oh, it's about the X.
Okay. It's about
Yeah.
x axis.
Yeah.
So because we have mx, my, mz. This is important because it's going to tell you is it going to be the bending moment, is it going to be the torsion. So this is how I need to find the direction of the moment. Fz times the y direction, which is 48 from the center of pipe. So mx is Fz 48 times 10 power negative 3. I should put 10 power 3 here because it's a kilonewton. I will get the moment 812.16 Newton meter. So just look at the direction of the force, and the moment is gonna make a bending in this direction. It's gonna bend the pipe something like this. Make sense? So if it's making the bending moment in this direction, just put your fingers in the direction of rotation. Your thumb is gonna show you the direction of the moment. It's gonna be in the positive x. So I'm just putting positive, just in case if you are looking for the sign of the moment. And now tell me which section is gonna see the critical section based on this.
Shouldn't that be negative clockwise? So if you look
head on to the x-axis.
Oh, it's right here. Yeah. They right. Yeah. Is this one?
It's making.
Don't use your left hand. Put your left hand there.
No, we are. Why it should be negative?
Because it's a clockwise on. The bending moment would be positive, but the actual force of the moment was
Yes, that's true. I mean, the force I didn't talk about. I mean, the force is acting about negative z. Force is acting about this direction. Positive z is in this direction. Forget about the sign. I mean. But what you need to see, it's gonna make the bending in this direction.
Yeah.
Can you see that?
Yeah.
Can it now, which section based on this bending moment is gonna be the critical section? Which section, not point? I didn't ask about the point. Section, I mean, which section over the pipe?
Oh, right by the wall.
Just based on this moment. Any section,
Right in the middle.
here or right at the middle or at the end. So like the compressive load. Because the entire of the beam is gonna see the same bending moment according to this force. Make sense?
Oh, because it's.
We were both.
We all.
All right. Now I'm moving from FC to FY. So we have something like this. Fy. What kind of stress can you see this force is gonna make? One moment about x-axis because Fy times the distance which is about z is making yz, it's making about x-axis. So Fy is 6.16. This section is the longest, I mean, it has the longest distance from the point D in z direction. Can you see that? So basically, based on this force, this section is gonna see the maximum bending moment. So mx max is gonna be 6.16 times 200 dB.
So is that 200 just the z component of that distance?
Yes, from
Okay.
D to B.
Okay.
This distance.
All right, I wasn't sure.
Because the phi axis is Z.
Yeah.
So if this distance is
How
given,
do we know that it's 200?
it's given.
He told us.
I forgot to mention at the beginning.
It's just not clear from the drawing.
Yes, it's not.
That's why he gave it.
He's not making
You,
this geometry.
you don't see the top portion of the problem. Even this one.
Okay.
I just. All right. It's gonna give me numbers. 1232 Newton meter. Can you see that this force times this distance is making bending moment, is bending the pipe in this direction? So for this force also it's making them bending in this direction. So basically both are making the moment in the same direction. So I can add them up. They both have x. The total m is gonna be 812.16 plus 1222 44.16 Newton meter. Now, where would be the critical section? Section, not points.
Well, no, all the forces, yeah, they're all the same.
No.
No, I mean this moment, the maximum moment occurs at this section. At each different section, you are gonna have the different distance from that section.
Oh.
So this is how you can decide about the critical section. For this, it doesn't matter which section we are in. We are gonna get the same moment, same stress for each section. But for this, depending on where you are, the moment is gonna be different. So it's gonna tell me that the section at point P is gonna be the critical section. Does it make sense?
Because all the other ones are equal along it.
No, because mx, due to this force, is varying over the beam.
I'm saying we don't have to do any other math.
No, you don't need.
Right, like if you had two that had different critical sections, you'd have to
Yes.
figure out. Okay.
Yeah, you have to do for both.
Right.
See where it's gonna be the critical section. But for this one, it's gonna be only section B. Any questions so far? Finding the critical section, I can say 60–70% of the problem. The rest is just working with the equations. All right. Section B is gonna be critical section. Can you tell me which point is gonna be the critical section? The critical point, sorry. 1, 2, 3, 4.
1 and 3
1 and 3, they are gonna see the same normal stress due to the bending moment. But we do have compressive stress due to the FZ.
But you're putting the bottom in tension, so it's a trend.
Yeah, okay.
Say it again.
The bottom is in tension.
Yes,
So
exactly.
you're actually.
So basically point 1 is gonna be the critical point because it's gonna add up to the stress coming from axial load. So point 1 is critical point. At critical section B. I forgot to say, this force is gonna be the transverse shear. So it's making transverse shear stress, which I gave you the table here. The cross section that we have is gonna look like this. For transverse shear stress, the maximum it occurs at the middle. At point 1 and point 3, the transverse shear is gonna be 0. Someone might say point 2 is gonna be critical section. We should find the tau max at point 2, which is gonna be the force times 2 divided by the area, and comparing with the normal stress that we get from this bending moment and this compressive load, which makes the normal stresses at point 1, and then compare these two. But typically, the tau max coming from the transfer shear is a very small number compared to the bending moment stress.
What's the pressure? What's transfer shear?
Say it again.
Quick refresher. What's transfer shear?
Transfer shear, I mean, if you have axial load, I mean, if you have transfer shear force, which is something like this, it's making transfer shear over the cross section. So the maximum transfer shear is gonna be the force divided by area times 2 for the cross section that we have.
So
Where-
what's the force of it trying to pull it up the wall?
Yes, basically, or the force is gonna cut the pipe.
Right. Okay.
So the maximum shear stress is gonna occur at this line, which is not our candidate for the bending moment. What I'm saying is, this transfer shear stress is significantly less than the normal stress that you will see on point 1.
And that occurs uniformly across the pipe?
Yes, because the force is gonna be the same, the transfer shear force is gonna be the same over the pipe from point A to B. So now, any questions so far? And the rest, I'm gonna find the normal stress due to the compressive load, the bending moment stress due to the bending moment, then I'm gonna add them up to see what would be the maximum normal stress. Yes, I mean, I just wanted to save time, but it's better that we test it on the small number. But what I'm saying is it's going to be significantly small number compared to the normal stress. On problem 3 of the exam 1, you had something like this. You were supposed to find the shear stress due to the transfer shear. Sigma, due to the axial load, is going to be Fz divided by the area. Fz is 16.92 times 10 power positive 3. Area is pi over 4. The outer diameter square, which is 60 millimeter square, minus inner diameter. With the thickness of 4, I subtract 2 thickness, which is going to be 8. 60 minus 8, 52. The inner radius is 52. If I do math, I will get negative 24 megapascal. Negative meaning it's a compressive stress.
That's sigma z.
Sigma z, yes. Whatever is the axis of time. So sigma z for bending moment is going to be mx y, which is half of the diameter, divided by iz. The total bending moment is 44.60. Half of the diameter is 30 millimeter. Divided by 60 divided by 2 is going to be 30. Iz is a c. If you mc divided by iz. Iz will be pi over 64. Outer diameter power 4 minus inner diameter power 4. M, C, half of the diameter, Iz. Pi divided by 64, D outer power 4 minus D in power 4. It's gonna give me negative, it's a compressive. I mean, we are looking for 0.1 anyway, so negative 221 megapascal. I got negative 24 here, negative 221 here. Sigma z at 0.1 is going to be negative 221 plus negative 24, negative 245 megapascal.
And that's 0.1
At B, yes. It's a point which is gonna see the maximum stress. Any questions so far? Now we should see which criteria, which failure criteria we can use. It's a ductile material 1020 outro. If you look at table 820, table 820, you will read S ultimate is 380 megapascal, yield strength is 210 megapascal. So maximum shear stress theory, distortion energy theory, and the last one is flow mode, ductile flow mode. So since we have still the ultimate strength for tensile and compressive would be the same, so we can use either maximum shear stress theory or distortion energy theory. If you want to be more conservative, you can use this. If you, for doing the analysis, we typically using the distortion energy theory. But in this problem, in this specific problem, you will get the same answer if you apply maximum shear stress theory or distortion energy theory. Maximum shear stress theory says tau max factor of safety. Factor of safety would be Sy divided by 2 divided by tau max. Or Sy divided by 2, tau max is sigma 1 minus sigma 3 divided by 2, or Sy divided by sigma 1 minus sigma 3. The only stress that we have on point 1 is the normal stress, compressive normal stress. So meaning no shear stress, no sigma 2, no sigma 1, just we have something like this. The other two stresses would be 0. So if I rank them, sigma 1 equals to sigma 2 equals to 0, sigma 3 equals to negative 245. Just plug in here, you will get factor of safety, Sy 210 divided by sigma 1 minus 245, you will get 0.85, 71.
Where did you get to 45?
Here, sigma 3. This is the stress element that we have. There is no other there is no shear stress, there is no other normal stresses. So it's telling me that I have these three principal normal stresses. That the smallest one is going to be negative 245, these two will be 0. So it's going to fail. The factor of safety is less than 1, it's going to fail based on this load.
Just remind us how you came to the decision to use the MSSP.
And I didn't assign which method you should use. If you want to be more conservative, you should use MSST. But typically for doing the analysis, we are doing the distortion energy theory, which is going to be this problem. I just wanted to show you that how this method is going to work. I'm going to work on the distortion energy theory as well. So
You're going to do that one too?
yes, but in this specific problem, we will get the same result. You will see, and I will explain why you will get the same result. Any question about this?
Can you, so like, I think, at least for me, the hardest part is figuring out which forces I actually need to solve for.
Which forces?
Or which, yeah, stresses, yeah. Will it be on the test something like this, that like, yeah, find all, because I still don't know what all stresses I was looking for in that spinning bobber that you gave us on the
Yes,
there's a lot of stuff going on.
it's the reason that I went step by step. The exam is gonna be something like this. Some forces apply like this to this component. I'm asking you to see which moments or torque is gonna develop based on those forces. I did my best to
Make it very simple.
yes.
They get a stick, and actually that's it, just one stick.
And one force.
Yeah, one force right on top.
It's better than it
People
should be the
still-
axial load.
People still like
Don't
that.
Please call it a B.
No, it's a stick.
Actually, I wanna know what the breaking force of the stick.
Yes.
And how many problems are gonna be on the test? Like there's
And two.
okay.
One marketing and one distortion and failure tolerance.
One marketing.
It's marketing. All right, distortion energy theory. The factor of safety was SY divided by 1 message stress. 1 message, we name it sigma O or V, whatever. So sigma O or 1 message stress can be obtained by sigma 1 squared plus sigma A. Sigma A times sigma B plus sigma B
There's a minus.
squared.
Yeah, minus.
Minus at the middle. Square root. I calculate 1 message stress, I compare with SY. Now, sigma A can be negative 245 or sigma B can be negative 245. In any case, the other one is going to be 0. Suppose sigma A is negative 245, this term and this term, they are going to be 0 because sigma B is 0. So sigma A square root is going to be 245. SY 210 divided by 245, you will get the same thing. 0.8571.
Could you remind us how you determine which sigmas are A?
It doesn't matter. I mean, usually I pick this as a point A and this as point B.
Also doesn't matter.
It doesn't matter which one. But 1, 2, 3 it matters. I'm talking about A and B. Coming
1, 2,
from
3 is just like biggest.
biggest, smallest. Any question about this? After tomorrow exam, I'm gonna compare this one with the problem that you will have on the exam, and you will see how they are kind of similar. So,
Just give us
no
that.
excuse.
Unclear if we should feel better or concerned, just like this is so fucked up. So. And that's all right.
Do you want me? I have two more problems. Do you want me to work on the bargaining or something like this? The other one. Bargaining. Okay. Well, I don't think we have enough time to go over the third problem. Almost the problem. All right. We have this steel pipe, this pipe, which has been supported by this cable. And force P is applied at the end of the pipe. The yield strength and modulus elasticity of the pipe is given. The pipe has the outer diameter of 2 inch. And the thickness of 0.5. 0.5 here, 0.5 here. It's going to be 1 inch inner diameter. 1 inch inner diameter, outer diameter is 2 inch. And we assume both ends are pinned. So pin. The horizontal force P is applied to this, and we would like to see what would be the largest amount of the force that we can apply without any buckling. And factor of safety should be 2. Good. You have worked on something like this on the homework problem. So the first thing that we should find from the static, this force is making force in this pipe and in this cable. What would be the axial force applied to the pipe? So it's going to be one force applied here, force P. Force P, the force should over the cable should be acting at the same direction, and the force on the pipe should be acting on the same direction of the pipe. So this angle is if this is theta, F, so let me this theta. F cosine of theta, F cosine of theta should be equal to P. This magnitude should be equal to this magnitude. And F sine of theta should be equal to P critical. This is how you can make sure the summation of the force are equal to 0 in x direction and y direction. This dividing by this, it's going to be P critical over P, it's going to be the tangent of theta. So P critical is going to be whatever is the P times the tangent of theta. This is how I just find the relation between this P and the force applied to pipe that we have. Now, I'll stop here, go to the buckling analysis. First, I will calculate L over K1, the point which is gonna tell me should I use Euler or should I use the Johnson. L over K less than L over K1 Johnson. Euler. So L over K1, it just depends on the specification of the material, which is 2 times C. C is the end condition. Here we have P, C is going to be 1. Pi square modulo of elasticity divided by yield strength. So no geometry is going to involve on L over K1. So 2 times 1 pi square E is 30 mega that's 10 power 6 psi divided by 43 kpsi. Kpsi means 10 power 2. L over K1 is going to be 117.35.
Why is C1?
It's a pin
With any
pin.
conditions.
It's an
Oh,
condition.
okay.
If it was fixed free, it's going to be 0.25. Now, I need to find L over K to see which criteria should be used. L is 12 feet. So 12 times 12, it's going to be 144 inch. The length should be in the units of inch. 12 feet. I just changed it to the inch. So now I'm calculating K. I would be A times K squared. I is the second momental area. A is the cross section. If I know these two, I can find K squared. K would be the square root of I over A. I have something like this. The I for this cross section is gonna be pi divided by 64, d outer power 4 minus d inner power 4. Outer diameter is 2 inches, yes. 2 power 4 minus 1 power. I will get 0.7363. Pi area is pi p power 4 minus d square for outer minus d inner square, pi over 4. Outer is 2 power 4 minus 1 power. It's 2.35.
You need power 2.
Power 2, thanks. Catching 2.35. Square, inch square. And this is inch. Now I can find K. 7363 divided by 2.35 is gonna be 0.558. I guess 0.558. Now find L over K. It's 144 divided by 0.558 is 257.6. 257.6 is greater than L over K1, so we are going to use the Euler criteria. In Euler criteria, we had P theoretical was C I squared E I L squared. C is 1, 3.14. E is 30 times 10 power 6 plus I, and I is 0.753.
And pi should be squared, right?
Pi is, yes, thank you. 60. This is I, L squared is 144 squared. The force is 105 pound or 105 K pound. 105 pound. 10 power 2 pound. So now, you are allowed to have 105 times 10 power 3, but factor of safety is 2. So you are allowed to apply just half of this. See how we can apply the factor of safety. P critical allowable. It's going to be critical divided by factor of safety. .5 10 power 3 pounds. Back to this, we are looking for P.
In our drawing there, we got PCR is going up. But isn't it gonna be put in compression?
The reaction to the,
Oh, so we just found the reaction.
yes, because
Okay.
this is how the column is gonna feel. I just wanted to find the P critical as a function of P, but this column is gonna see the reaction. So I'm looking for P. P critical would be P times the tangent of theta, or P would be P critical divided by, or P critical allowable divided by the tangent of theta. This is 52.5. 10 power 3, the tangent of this angle. Tangent of this angle. This angle of the is going to be same as this angle. Can you see that? The angle that I'm talking about is this angle, which is going to be equal to this one. So the tangent of this is going to be 12 divided by 5. It's going to be 2.1 thousand pounds. So you are allowed to apply to about 2100 pound force in vertical horizontal direction. And this was another problem that I gave. I'm not sure if it was last year or year before that. one force applied here, we would like to find the factor of safety based on distortion inventory and maximum shear stress. Again, you need to find critical section based on the loads that or stresses that these forces may create on this one. Good? Alright, so see you tomorrow at 2:10 science center.